So more on complex ions here, and we're going to deal with the shapes of complex ions now. And in the diagram here you can see a tetrahedral shape where in the middle here we have the metal ion, and on the outside we have 4 ligands, 2 different types of ligands, and in this case arranged in a tetrahedral shape with a bond angle of about 109 degrees. What we're going to do in this lesson is work out all the different shapes and what determines the shapes. So this first lesson objective here implies that the shapes of the complex ions depend on the coordination number. All right, so we're going to look at coordination numbers of 2, 4 and 6 and see what shapes those coordination numbers lead to. And then lastly, we're going to have a look at haemoglobin, which is a complex ion that exists in our body, transporting oxygen, water vapor, and we'll have a look at that. So first of all, let's have a look at complex ions that contain 6 coordinate bonds, and they have an octahedral shape. So 6 coordinate bonds, octahedral. Okay, let's have a look at an example. Example would be here, we've got cobalt hexa aqua complex. So let's write the formula of this. So we've got a cobalt, our ligand is water, we have 6 of them, and our complex has a charge of 2+. So we have cobalt hexa aqua complex here, and in a different view we might see that as this, slightly more easy to see its shape. Okay, so we can see this bond angle 90 degrees, this bond angle 90 degrees, all the bond angles are 90 degrees. So that's what we have to remember. In shapes such as this one, which we're going to call octahedral, all the bond angles are 90 degrees. And just on the right there we have some sort of 3D filled in shape of an octahedral molecule, where the ends, the corners here would be where the molecules are, the ligands are, and in the middle of that shape would be the central metal ion. Okay, so 90 degrees for 6 coordinate bonds and octahedral shape. Okay, so moving on, complex ions that contain 4 coordinate bonds, they usually, not always, usually have a tetrahedral shape. So remember that, 4 coordinate bonds, tetrahedral. Let's have a look at an example. All right, so when our ligand is slightly bigger, like chloride rather, 6 of them can't fit round, so 4 of them fit round instead, and when 4 of them fit round, you usually get a tetrahedral shape. And this example here is tetrachloride copper complex, and so in a tetrahedral case, especially here when all our ligands are the same, our bond angles will be about 109 degrees. But if we have 2 different ligands, then it might vary from 109 a little bit. Okay, so on the left we have copper, on the right we have cobalt. Both of them are 4 coordinate bonds, but you would notice them as different colors because the copper one would be seen as yellow and the cobalt one would be seen as blue. Now we said that when we've got 4 coordinate bonds it's usually tetrahedral, but in some circumstances 4 coordinate bonds, coordination number 4, 4 coordinate bonds gives us a square planar shape, as in a drug called Cisplatin, of which we've got a diagram here. So Cisplatin is a cancer drug, and it's got a platinum central ion, and it's got coordination number 4. So 2 of the bonds are to chloride ligands, and 2 of them are to ammonia ligands. And in Cisplatin, the 2 chloride ions are on the same side of the molecule, and obviously the ammonia ligands have to be on the same side as well. You can get Cisplatin, which is not a cancer drug, in which case the ligands would be arranged alternately around the molecule. So that's the Cisplatin, and because of the different sizes of the ligands, they form a square planar shape instead of a tetrahedral shape. And this central platinum ion would be 2 plus, and each chloride ion, of course, is chloride 1 minus, which gives us a neutral charge for the complex overall. Okay, so now we've dealt with the coordination number. Let's have a look at the last one. So the last coordination number that we need to know the shape of is coordination number 2. And some silver complexes that have 2 coordinate bonds, they have a linear shape. And when silver is dissolved in ammonia, you get this complex here with the silver ion. It's a 1 plus ion in the middle, and you have ammonia where the nitrogen has a lone pair, and that forms a coordinate bond with the silver ion, and that happens with 2 ammonia molecules, and this lone pair on this nitrogen forms another one, and so that's as you can see, a linear shape with this bond angle being 180 degrees. Okay, so 2 coordinate bonds, linear. So before we go on to have a look at haemoglobin, let's just summarize our shapes and link them to the coordination numbers, and do it in a way that enables us to memorize it. So we can memorize the shapes with the mnemonic LOST. Okay, so we've got L-O-S-T like this, and so L stands for linear, O stands for octahedral, S stands for square planar, and T, of course, stands for tetrahedral. And we have linear shapes, and let me put the column heading down here. So we have a coordination number. So we have linear shapes when the coordination number is 2. We've got 2 coordinate bonds. We have octahedral when the coordination number is 6. We have 6 coordinate bonds. And both square planar and tetrahedral are 4 coordinate bonds, with tetrahedral being our usual one and square planar being in unusual circumstances like cisplatin. And let's just list out our bond angles. So with our tetrahedral, it's going to be about 109 degrees. And the square planar bond angle will be 90 degrees. And as with the octahedral, be 90 degrees. And of course, the linear would be 180 degrees. So hopefully that helps you remember the shapes and the bond angles. So lastly, let's have a look at haemoglobin. So, and we may know that haemoglobin is a protein found in the body that helps to transport oxygen from the lungs to the muscles, and also it will, on the way back, transport water from the muscles back to the lungs so they can be expelled in our breath. So let's have a look at some red blood cells. So they are red. Why are they red? Because in the middle of the haemoglobin is an iron. It's Fe2 plus. All right, so in the middle here we've got Fe2 plus ions, and the actual complex looks like this. All right, pretty complicated. There's our Fe2 plus ion in the middle, and it's surrounded by this ring. It's called a porphyrin ring, also known as heme, as in hemoglobin, and that is the ring that we can see around here, with the lone pairs on the nitrogens making these coordinate bonds. All right, so if you can actually imagine that in this ring in the horizontal plane, let's try and draw that. So we've got an Fe2 plus ion in the middle, and we're going to have nitrogen coming back from behind the page. We've got a nitrogen here going from out of the page back into the page, as we have here. And we've got another nitrogen at the back coming forwards to that ion. And then we've got this sort of in a ring, a horizontal ring, like so. We've also got another molecule that's attached via a coordinate bond from another nitrogen atom, with this nitrogen atom being part of a big protein called globin. Right, so that's where hemoglobin comes from. But you notice that if this complex centered around the ion was octahedral in shape, it would have an empty space for another coordinate bond here, and that is where the oxygen that we breathe in. All right, so there's a lone pair on an oxygen molecule, and that would, just to draw it as an oxygen atom for the purposes here. So when we breathe it in, the lone pair on an oxygen molecule makes a coordinate bond with the ion in the complex, and then that is transported via the blood to where it needs to go. And then when it needs to come back, instead of having an oxygen there, you're going to transport a water molecule on the way back. So water being a product of respiration. So from the cells that respire, they're going to emit or make water molecules in that respiration reaction, and those water molecules are going to be excreted from the body by means of the oxygen of the water making this coordinate bond with hemoglobin. So that's how hemoglobin transports oxygen and water vapor in and out of the body. But also it's worth noting that in a fire, for example, when there's incomplete combustion and you know, the carbon monoxide is present, there is a lone pair on, that's a carbon monoxide molecule now, there is a lone pair on the oxygen of carbon monoxide that makes a very strong bond with hemoglobin. Very strong coordinate bond. That's quite a stable molecule with when carbon monoxide is bonded to hemoglobin. And what the effect of that is that it doesn't leave, so it stays there. So it blocks oxygen from joining a hemoglobin molecule, and that's how we get poisoned by carbon monoxide, because it blocks the access of oxygen to hemoglobin. Okay, so that's what you need to know about hemoglobin, and that finishes this little video on mainly on shapes of complexes.